All right, today is lesson 4.8 from your algebra book. And our big idea is that placing "and" between two sentences means that you want the intersection of their solutions. Placing "or" means that you want the union of their solutions. Okay, so we're going to talk further of that in a second. So a compound sentence is any sentence containing two or more sentences that are linked by the words "and" or. So if you want both things to be true at the same time, that's "and." Or if you just want either one of them, possibly both at the same time, but just one is fine, then that's your "or." So our intersection would be our "and our union would be our "or." So an intersection, we need both things to be true at the same time. So this is kind of where two solutions overlap. Must be in both. So on a line graph, okay, if it's more than this number and less than this number, okay, that would be an intersection. It's in both. And for a union, this is your "or." So in either solution. There are symbols for these. So your intersection is kind of an upside down U, and your union is your up U. So this means "or." So in either or. Intersection means it must be in both. And so for example, let's make some quick diagrams. So this box is going to represent all students. And we're going to draw two circles that overlap. And let's do two of these so we can compare the "and" the "or." All right, so the box represents all students in the school. And we're going to make this circle represent kids that play sports. This circle is kids in the band. So if this is your "and" or your intersection, we are just representing students that play sports and are in the band. So if you look, that's going to be our overlap. So in order for this to be an intersection, both have to be true. So they have to be kids that play sports, so they have to be in this circle, but they also have to be in the band, so they have to be in this circle. So if they're just in band, no good. If they're just in sports, no good. This is your "and." Whereas your "or your union can be either one. So it does include both. It could be both. So it's still those students. But if a kid is just in band, that counts. Or if they just play a sport, that counts. So if I say I want students that play a sport or are in the band, it's a lot more than if I said I want students who are in sports and the band. Okay, so there's a kind of a visual representation. So mathematically now, what is this going to look like? So example number 1, we're going to graph x is greater than 8. And we're going to be graphing x as -3 as well. So let's put both of these points on our graph. So -3 down here, +8 up here. If we're graphing x is greater than 8, it's going to be an open circle on 8 because it's not included. And greater than would be this direction. Now let's graph right underneath of it. X is less than or equal to -3 on a similar graph. So first of all, it's going to be a filled in circle, and x is less than numbers are this way. Now it says graph the union, which again is the "or." Union, or. So either one can be true. So x can be greater than 8, or x can be less than -3, both fit this solution set. So that means both are included. So anything down here is part of the solution set, or anything up here is part of the solution set. So the only numbers that are not part of the solution set are ones that don't fit either, which would obviously in this case be between the two. Now it says graph the intersection. Intersection means both need to be true. So x needs to be greater than 8, and it also needs to be less than -3. It needs to be both and both. That's the symbol. So what numbers are less than -3 and also greater than 8? Well, none. There is no solution here. There's no overlap. Okay, neither one of these lines or solutions will ever overlap. So in this case, there is no intersection. All right, let's take a look at example number 2. So we're going to solve and graph this. So this is the first time we're kind of seeing two inequalities written in one sentence. So we're really looking at this expression, 5m plus 4. And we want to know when is it greater than or equal to -8 and less than 19. So here's how we can work this. You could think of them as separate. You could cover this up and work this one out. You could cover this up and work this one out. You can actually do it at the same time. So that's what we're going to look at first here. So if I attack this at the same time, I'm still trying to get m by itself. I want to know what letters for m or what values for m make it greater than or equal to -8 or less than 19. What values of m? So I got to get m by itself. So that means just like normal, I'm going to minus this 4. Well, that needs to be on all sides of your inequalities. So I'm actually going to minus 4 in 3 spots now. Once in each location around my inequalities. So it cancels here, which just leaves me 5m. I have not multiplied or divided by a negative, so none of my inequalities will change direction. -8 minus 4 is -12. 19 minus 4 is 15. Almost done. So now I want to divide m by 5. So I'm allowed to do that as long as I do it once in each spot. So now m is by itself. Again, I did not multiply by a negative, so nothing moves. 15 divided by 5 is 3. So m needs to be less than 3. M needs to be greater than or equal to. Now, if you divide this, it's a nice decimal. -2.4. So the numbers that I can plug in that will be true for this original sentence for 5m plus 4 that give you a value that's greater than or equal to -8 or less than 19, or any value of m that's greater than or equal to -2.4 and is also less than 3. This needs to be both. Okay, both need to be true. Not just any number greater than -2.4. You can't go up to 100. And not just any number that's less than 3. You can't go down to -10. It needs to be in both of these solution sets. Okay, so this is going to represent, not a union, an intersection. This is an and. So where do these two solutions intersect? Okay, it can't be either or. You're not just combining the two solutions. It has to be where they intersect. So this is going to represent an intersection. So when we graph this, we're only graphing the part of the solutions that fit both of these. So if I put -2.4 down here and 3 up here, if I was just going to graph m is greater than or equal to -2.4, I'm going to fill in my circle, and greater than would go this direction, and I'd shade, and it'd go on forever. Any number greater than 2.4 would go on forever. And m being less than 3, I'd have an open circle, and then it would go less than forever. But we need both of these to be true at the same time. So if I continued 2.4 forever, it wouldn't be part of the less than 3 solution. And if I continued the less than 3 solution forever, it wouldn't be part of the greater than or equal to -2.4. So the intersection of these two greater than 2.4 all the way up till 3 and less than 3 all the way down to negative 2.4 looks like this. So this is my intersection interval. This right here, if they ask for an interval, that's what it is. This is what they're looking for. So in terms of symbols, m being greater than or equal to negative 2.4 or less than 3, okay, that's the interval, and then this is what the graph looks like. So now this was an intersection. Let's look at a union. So if you flip this over, see the word or. So this is your union, which is this symbol. So we're going to solve and graph this. So you'll notice these are separate. So we're going to solve them separately. So first of all, over here, I've got y on both sides. Now I could get rid of the smaller of the two, but now that's going to leave me an empty side. So in this case, I'm going to subtract 13y from both sides so that I don't have an empty side. So 84, have not multiplied or divided by a negative, so I'm going to leave it alone, is greater than negative 12y, 1 minus 13. And then I'm going to divide by negative 12. I'm dividing by a negative, so I do need to flip my inequality. It's very important. So y greater than, and this division gives you negative 7. So let's graph this one just individually. So here's 0. Here's negative 7. Y needs to be greater than negative 7. So not included in. So everything greater on forever. Now that's not the solution to this whole problem. That's just the first one. So now let's complete this one. And for the sake of space, I'm going to move it over. Now this one, the smaller of the two, if I eliminate it, it doesn't clear out a side. So I'm just going to go ahead and do that. So I have 9. I didn't multiply or divide by a negative, so leave it alone. 3y. I'm going to divide by 3. It's a positive, so I don't flip anything. So y must be greater than 3. If I graphed just that, here's 0, here's 3. Okay, it would look like this and go on forever. Now, the solution to this problem is either or. So any number that's in the first solution set or the second one. It doesn't have to be in both of them. So if I'm going to graph now my total solution, and let's say I put both these numbers on my graph, it can be in either one. So really I want to put both of these on there. So from 3 higher, that's in both of them, because if I take negative 7 and I go to the greater side, I'll get up into these. So that's definitely part of it. But this isn't an intersection. It doesn't have to be in both. If it was in both, then it would only be this top section. But it's either or. So any of these that are in the solution set for y greater than negative 7 count. As long as it's in one of these, since it's an either or a union, then it's part of the overall solution. So our solution starts all the way down at negative 7, and then it actually goes on forever this way. Notice I didn't put a circle or anything on 3. There's no need to. It's part of the solution. So the only numbers that are not part of either one, sometimes it's easier to think about what numbers are not in the solution, are ones that are less than negative 7. As long as it's greater than negative 7, it's going to be in this solution, and it's automatically going to be in this one as well, because we're going to pass 3 as we draw this arrow going this way. Okay, so since it's a union, either or, the solution set includes both of them. We do have some overlap. They go the same direction. So it's really any number greater than negative 7. All right, example 4 now. So a family purchased some neon Tetra fish, and they put them in their new fish tank. They look on the internet to see what temperature they should set the tank at. One site wrote to keep the water temperature between 72 and 78. A different site said it should be between 68 and 74, and a third site wrote between 73 and 81. So they all varied a little bit. So first of all, let's write each website's temperature range as an interval using T to represent the temperature of the tank. So remember, the intervals look like this. You're going to have your variable in the middle, and it's going to say basically it goes from here to here. So T is going to go in the middle. And for site 1, they said 72 to 78. Okay, so T needs to be greater than or equal to 72, or less than or equal to 78. T being the temperature. So site 1 said anywhere from 72 to 78 is good. 72 is included, so the equals. 78 is included. Okay, so it's got to be between the two. And then for site 2 now, the water needs to be between 68 and 74. So T needs to be greater than or equal to 68, less than or equal to 74. Whoops. And the last one, again, it includes both the smallest and the largest number they gave. So it has to go from 73 up to 81 at site 3. Both these numbers count plus everything in between. So numbers greater than 73, less than 81, or those numbers, it could be equal. So let's graph these real quick. So your first one, let's go ahead and use all these numbers up here. So if this was the smallest number we need, 68, we got to get all the way up to 81. So 72, let's put it right here. We're going to need a 74. It's going to be a little closer. So 72, 74, 73 is also going to be in here, right? So we're going to need a 73, 72, 73, 74. There's going to be a 78, a little bit higher. And our biggest number is going to be at 81. So real quick, let's recreate this so we can kind of examine all three of these. Okay, so site 1 goes from 72 to 78. So it includes 72, and it includes 78, and everything between it. Site 2, same idea, but goes from 68, including it, up to 74, including it. And last but not least, site 3, it's going to go from 73, including it, up to 81. So there's our three different sites. So now answer the question. To be safe, what temperature should the family keep the tank at? So if in general these all worked out for the individual families that did it, to be safe, we don't know. This person who said 73 to 81, maybe they actually kept theirs down here closer to 73. Maybe this person who said 72 to 78 actually was in here close to 73. And this person was also close to 73. That sounds like it'd be the safest bet for me, is do something that works for all three people. If you keep it down at 68, well, we don't know if that would have worked for this person or this person. Maybe only this one, possibly. So to make our safest prediction here, we want to find the situation that kind of works for all of them. So this one starts at 73 and doesn't include 72. So it's kind of going to start at 73. And then the farthest I can go up where it's included in all of them is right here at 74, because it's included in this. It's included here, and I can't go any higher because it would no longer be included in site 2. Okay, so if I'm going to write an interval here of the possible solution set, I would go anywhere from 73 to 74. Now think about, does this represent a union or an intersection? Okay, if it was a union, that would be the or. That means I could put it in any one of these. So they'd all be included. So we'd actually have to go all the way from 68 to 81. But if it's an intersection, it needs to be included as an and be included in all three. So the only part of these solution sets that show up in all three is when the temperature is greater than or equal to 73 or less than or equal to 74.